Hello, it's Keith here, and this is lesson 87 of the platform-specific series of my Z80 assembly programming tutorials. We're looking at the MSX today. The example is MSX1, but what we're going to be discussing works fine on MSX2 as well. We're going to be discussing interrupts, and what we're going to do is we're going to get sound playing via my ChibiTracks music player via interrupts on the MSX systems. Now, what we're going to do today is we're going to assume we're running from a ROM cartridge because that's the harder method of the two options. So that's what we're going to do. And as I say, while we're looking at MSX1, it works fine on MSX2. And if you don't want to use ChibiTracks, that's fine. If you're using Arcus Tracker, everything I'm discussing today will work just fine there as well. Now, as an added bonus, we're also going to discuss the turbo mode on Turbo R and WSX. And the reason we're doing that is the WSX actually alters the pitches of the music playing because of the way the hardware works when it switches to its 6 MHz processor mode. And so I've put a compensation in ChibiTracks to compensate for that, and we're going to just check that out and discuss it as well because I thought it was as good a time as any to include it in here. Okay, well, let's go over to our code. Let's check it out, and let's also hear what's we're going to be seeing today. So let's just run our example here. If we select, I'm going to run it on the MSX2. Okay. So here's our MSX2 booting up here. So here is the example. This is an extension of the previous example, and the point I was trying to make here was really that we've now got graphics and we've got sound. So we've got the and joystick reading, of course, and so we've got basically the template for an entire project. Now, as I say, we're going to be using interrupts to time the music. That's the best way of making music play in a consistent way, irrespective of what our game is doing. The problem is that interrupt mode 1, which is really the best interrupt mode for most purposes, executes a call to memory address 0038 when the interrupt occurs. Now, we're running from ROM, and that is actually part of the firmware. So we can't change that memory address to put a jump in, which is what we would do on a lot of systems. And what I did in Chibi, the game, that actually worked with RAM, so it paged out all of the ROM and paged RAM into those areas, but you can only do that on a 64K system. And we may not have 64K, or we may just want to not do that. So this time we're going to do the full job of working with the firmware. Now, basically, what we need to do to get the firmware to work for us is we need to insert a jump in part of the RAM area that is sort of predefined as the sort of chain on point for custom interrupt handlers. So the memory address FD9A is the point that we are able to put our own interrupt handler in and sort of chain it on to the end of the other interrupt handlers, and some other interrupt handlers do actually occur. Some system ones do occur after this runs. So all we do is we put the equivalent of a jump command, that's what that is there, that's a jump command, and then we put the address of our interrupt handler in, and we put those 3 bytes at FD9A. Now, our interrupt handler itself is actually very small because the vast majority of the work is being done by the system, although to be honest, if I was replacing the system interrupt handler in entirety, I'd only add 2 extra commands to this. So here is the interrupt handler for ChibiTracks. ChibiTracks doesn't use the shadow registers and it doesn't use IY, so we're only backing up BCD, HL and IX, and we're using the shadow accumulator here because it's free. The rest of my code never uses that, so we're using that in the interrupt handler here. Now, if we were replacing the RAM in the low area, the only changes we'd need to make are 2 things. We'd need to enable interrupts at the end of our routine before we returned, and we'd also need to read in from the control port. Now, when we read in the status register on the control port via a command like this, that actually clears the interrupt. If we don't do that and we're not using the firmware interrupt handler, the interrupt would fire again immediately, and that would mean that our game would lock up, we'd never see our game running, and our music would play extremely fast. So those are 2 things you would need to do if you were writing an entire interrupt handler. But the return here actually goes back to the firmware interrupt handler and it's finishing the job for us. So we don't need to do that here. We just need to worry about our music playing. So that's all we're doing there. Now, one other thing we do need to do though is we need to tell the hardware to actually generate interrupts. Now, the interrupts are being executed by VBlank. VBlank is causing the interrupt, and so what we need to do is we need to get the hardware to actually create the interrupt. And it's actually this bit here, bit 5 of VDP register 1 here is the one generating the interrupts. Now, if I just change this, if I change this 1 to a 0 here, I've just changed that to a 0, and I run this again, our program will load up. But what we will actually get is we will get no music. So here's our program starting. And now we've got no sound. And for some reason it's actually crashed. I don't quite know why that's happened. It shouldn't do, but for whatever reason it has. So that's what happens when That's what happens if we don't enable the interrupt. It's an easy gotcha if you're just getting started and you've created what you think is a working interrupt handler. You may be correct, and it's just not working because you've forgotten to enable the interrupt at the VDP level. Now, one other thing you need to bear in mind when you're running interrupts is you need to make sure the interrupts are disabled when commands that are going to cause problems for your interrupts are occurring. Now, there's a couple of things that I do within this code that will cause problems for the interrupt. Now, the first thing is selecting a VDP write address. If the interrupt occurred between these two, that would cause those to malfunction, and that would mean the wrong address was selected. I had that problem on the master system. Another problem that you need to watch for in this code is stack misuse. I'm misusing the stack as a fast reading pointer, so that means that if an interrupt occurs, that will cause problems. There is some complex tricks you can do to avoid that, but for at a simplistic level, just if you're just getting started, assume that if you're doing stack misuse, disable interrupts. And to be honest, if you're unsure, disable interrupts and enable them later is safest anyway, because on the MSX, the interrupts actually occur whenever interrupts are re-enabled. You won't miss any if you disable them for an extended period, so it's not too much of a problem. On a system like the Spectrum, that's not the case, and you will miss interrupts and your sound will play very slowly if you disable them too much. One other gotcha that you do need to watch is the joystick. Now, the joystick is actually connected to the AY sound chip, and so because my interrupt handler is playing sound, it's messing with the sound chip, and that will mess with the joystick reading. So we're disabling interrupts for our joystick reading routine and re-enabling them at the end. So that's just another thing that would cause problems. Now, ChibiTracks itself has a few dependencies. So we've got these parts of the player. It's just split into 3 ASM files. We've got the platform-specific sound driver, so that's to play the AY sound. And we've got a binary file that we want to play. Now, at the start of the code, we're defining some RAM that uses about 128 bytes of RAM, and we're defining various pointers within there to the various variables that the player needs. It's just convenient to just tag them onto the end of the Chibi Sound RAM, which is used for the sound driver. Now, the MSX has a special one, which is Chibi Octave address. This is an optional one that no other system uses, and this is so that we can remap the octave for the WSX, which has that 6 MHz mode, which causes a pitch shift. So we're going to use that specifically for that one system. No other system needs it. We've got two options here as well. Relocation is to do with the binary files. When we export from ChibiTracker, we export a binary load address, but if we want to load it to a different address, we can do so as long as relocation is enabled. It's a little bit slower, adds a few extra bytes to the program code, but I would suggest you leave that re-enabled because it's a lot easier. Speed change is another function, and this is to change the playback speed at playtime when the code is actually playing the file. You might want to do this if your music is playing on 50 and 60 Hz systems and you want to tweak the speed to make it play at the same speed, or if your game makes the music play faster if the player is running out of time, that kind of thing. But the binary file I'm using today has actually got the speed pre-multiplied into it, which means that we can disable allow speed change, but when we don't really have any options left for changing the speed, we could override the speed, but only very crudely. If we change the speed to 2, we would literally halve the speed of the song, whereas before I think the default speed's like 5 and we can change it to 6 to make it just very slightly slower. But as I say, with the pre-multiplied speed, we have a smaller compiled program, but we have that song speed change doesn't really work very well. Now, when we want to start our song, first what we need to do is we need to initialize the sound driver. We only need to do that once. That's initializing the AY register variables and things for Chibi Sound Pro. We then load the address of the song we want to play to Songbase, and we run start song. The rest of the work is done by our interrupt handler. That is the only other command we need to run to update the sound. That's the entire job done. So that's how we're playing our music. Now, what we're going to look at now is the actual turbo mode. Now, we're running this CPU turbo on option here. Now, on a system with no turbo mode, most MSXs, that will do nothing. On the WSX types, that will switch us into 6 MHz mode, and on the Turbo R, we will enable the R800 processor, which is much faster. It's arguable how fast it is. It depends what you're doing. If you're doing raw CPU functions, you may see a speed increase of 3 or 4 times. In some stuff, it's only about 1.5 times. Depends how limited by the video hardware you are. If you've got a V9K type video chip like the Chibi Akumas could use, you get a huge speed boost on that system, because that is very processor based then, not being held up by the graphics hardware. So here we're turning the CPU's acceleration on if it exists. We're then loading the default octave and we're comparing the accumulator, which is returned by this, to 247. Now, if that is returned as 247, then we're on a WSX type system in 6 MHz mode, and so we're shifting the octave to compensate for the pitch change here. Now, what we need to do though is see how this CPU turbo on is working, and we've got that in a separate file. Here's the file we're looking at here. So this actually does two different options for the two different pieces of hardware. So first of all, we need to check and see if we're using a Turbo R, and I understand the best way of doing that is to read in a byte from memory address 180 and to compare it to C3 in hexadecimal. And if it is C3, then basically we have a Turbo R piece of hardware. And to turn the Turbo R on, what we do, the processor on, is we call memory address 0180 and we load a byte into the accumulator, and the byte 82 will turn on the caching of the ROM option, and it will turn on the faster processor. So that, I believe, is generally the best option. And so in that case, we will run that, and that will turn the processor on to fast mode. So that's what we're doing there. Now, what we're doing after that is we're then going to actually sort of check and see if we've got a WSX type. There's a couple of different brands of WSX. There's a couple of different models of WSX, but they all have the 6 MHz processor. And what we can do for that is we want to check and see if we're using a Panasonic type machine. And so we're loading in from memory address 002D and comparing to the value 2. Now, if we don't find a 2 at that address, we're not on a WSX. But if we do find a 2, that doesn't necessarily mean we are on a WSX, and we will now need to continue to test the hardware type. So what we're going to do is load the accumulator with the value 8 and out that to port 40. We then read in back from port 40, and we should get the complement of that 8 value, which is 247. Now, if we get a value of 247, we are on a WSX. If we don't, then we're not. If we're not, we're simply returning back to here. We're popping the original accumulator flag here. Now, if we have got a WSX though, what we're going to do is we're going to write the value 0 to port 41 in hexadecimal. That will turn on the approximately 6 MHz speed mode, which is a fair boost to the processor speed of the Z80. And then what we're doing here is we're just clearing the original value that we loaded in here, and we're now writing the accumulator with 247, and that is just so that our calling routine can detect the hardware. Now, I should point out, because this will catch you out, it caught me out when I was writing Chibi-Akumas, the version of OpenMSX I'm using does not emulate the pitch shift of the faster processor. So when I was writing the game, I didn't realize there was anything wrong, and it was only when I was testing it on a real WSX I noticed the pitch was crazy, and I found out, oh yeah, there's this pitch shift and it's not emulated. So what we're going to do now is we're going to run OpenMSX with a WSX processor, and you will actually hear that the pitch will shift. And the reason the pitch is shifting is because actually the pitch shift isn't properly represented within the hardware. So what we're going to do here is we're going to run and so we're running now on a WSX processor here. And so you can hear that the pitch is actually different, but as I say, if you were running on real hardware, it should be about the same as it was, because you're hearing the compensation and you're not hearing the way the hardware works differently because it's not emulated by this emulator. So there we go. So that's how we can write an interrupt handler. That's a brief introduction to ChibiTracks, and that's also how we can turn on the faster processor. And I would really honestly suggest you turn on the faster processor if you're writing a game, because there's no significant disadvantage to it. You will get a slight boost to your game speed. Usually you won't get enough of a boost to make the game unplayable, because as I say, the Turbo R on the MSX2 is usually limited by the VDP hardware, so really you're just getting a very slight increase to your game speed. It's not like it's going to run at 10 times the speed or anything. It's only if you've got the V9K that might become a problem. Anyway, there we go. As I always say, go to the website, download the build scripts and the source code, and have some fun with it. Do whatever you want with it. I hope you've enjoyed this today. Thanks for watching, and goodbye. Let's wait for the advert to go. There we go. Bye now.